To represent text in artificial intelligence, we need to tackle some unique challenges that text presents compared to other data forms like images or structured tables. You see, unlike those concrete visual elements, language is, abstract, variable, and highly context-sensitive. There's just no direct correlation between the meaning of a word and its written representation, which makes it quite the puzzle for computers to decode. So, how do we effectively navigate this complexity? Well, let's unpack it together. First off, we must consider the nuances of human language, with all its idioms and expressions that can change meaning based on context. Imagine trying to teach a computer about humor. It's like asking it to solve a riddle. Additionally, we have to think about how language varies across different cultures and regions. So, as we dig deeper into this topic, we'll explore how to represent text in a way that allows AI to understand and interact with it more like a human would. All right, let's dive deeper, shall we? Now, let's implement the following code to generate word embeddings using the Word2Vec model from the GenSim library. First up, we need to import the required modules, specifically Word2Vec and NLTK. Now, NLTK is fantastic for natural language processing tasks, so let's make sure we've got the Punkt tokenizer downloaded and ready to go. This tokenizer is key because it helps us break down our sentences into manageable tokens, which is a crucial step before we train our model. Next, we'll define a list of sentences. That's where the fun begins, making sure each one is tokenized into words using nltk.wordTokenize. This creates a structured format that our Word2Vec model can work with smoothly. Now, moving ahead, we're going to train the Word2Vec model. Just pass those tokenized sentences to it, and don't forget to specify some important parameters. For instance, there's vector size, which decides the dimensionality of the embeddings, and then we've got window, which defines the maximum distance between the current and predicted word within a sentence. Once that's done, we save our model to a file for future use. Finally, let's demonstrate how to access the vector representation for a specific word. How about artificial? This will illustrate just how we can leverage our embeddings for various NLP applications, showcasing the power behind it all. Now, let's implement the following code to load glove embeddings for our NLP projects. The first step is to define a function called loadGloveModel, which takes a file path as an argument. Inside this function, we initiate an empty dictionary, GloveModel, where we'll store our word embeddings. Next, we open the specified Glove file in read mode. With each line in the file, we split it into separate components, where the first element is the word and the remaining elements represent the corresponding vector values. We then convert these vector values into a NumPy array for efficient numerical operations. Each word and its vector gets stored in our GloveModel dictionary for quick access. After defining our function, we can call it with the file path of a Glove dataset, like glove.6b.50d.txt. This will populate the GloveModel dictionary with embeddings that we can use throughout our NLP tasks. Finally, we can effortlessly access specific word embeddings by referencing the dictionary, allowing for efficient retrieval of vector representations needed for various applications. Now, what's interesting here is the clear ascending pattern that shows a progression from the sparse, high-dimensional, and semantically naive representations, think of one-hot encoding, toward increasingly informative and dense vector representations like Word2Vec. So, what can we conclude from this? Well, one-hot encoding, while the simplest, offers the lowest representational complexity and, unfortunately, lacks any semantic relationships. Now, when we move to the bag of words method, it adds some frequency information, but it still discards the order of words. Then we have TF-IDF, which increases representational nuance by weighing words according to their importance in the entire corpus, helping us to distinguish those truly informative tokens. And finally, Word2Vec takes the cake, representing the highest complexity shown here, providing dense, learned embeddings that really capture those semantic similarities and contextual relationships between words. This ordering highlights an important trade-off between simplicity and representational power. You see, simpler methods can be computationally cheaper and sufficient for smaller or more constrained tasks. But for tasks that require a deeper understanding of meaning and relationships, more complex embeddings like Word2Vec deliver a richer semantic structure, which ultimately motivates the move to even more advanced contextualized models. Now, let's see how we can implement BERT for contextualized embeddings. First, we're going to import the necessary classes from the Transformers library, which gives us access to pre-trained models like BERT that are super easy to use. Next, we'll load the BERT tokenizer and model specified as BERT base uncased. The tokenizer, well, it processes our input text by converting it into tokens that the model can understand, ensuring that our text is in the right format for BERT. Now let's tokenize the input text, which describes how AI is reshaping industries. By using this tokenizer, we prepare our data for the model, returning it as tensors suitable for PyTorch. Once our input is ready, we proceed to get the embeddings. Here, we use the model to process our tokens without tracking gradients, which is great for efficiency when we're just after outputs. After running the BERT model, we'll obtain the last hidden states, which are the contextualized embeddings for each token. These last hidden states are crucial as they encapsulate rich semantic information that reflects the surrounding context of each word. This nuance is invaluable for tasks like sentiment analysis and conversation modeling. Finally, we'll print these embeddings to visualize the contextual representations that BERT so wonderfully provides. Now, let's implement a text pre-processing function that will clean and prepare our text for analysis by an NLP model. The process starts by importing the necessary libraries. We need RE for regular expressions, and then there's NLTK's stop words and WordNet lematizer for filtering and normalizing words. Oh, and don't forget, we also need to download those required stop words and WordNet resources for lemmatization. Next up, the pre-processed text function begins by converting the input text to lowercase to maintain uniformity. This is crucial, you know? Following that, we use a regular expression to whisk away any punctuation or numbers, ensuring we're focusing solely on alphabetic characters and spaces. Once we've cleaned that up, we split the cleaned text into individual tokens, allowing us to work with each word separately. In the next step, we filter out common stop words. Those are the words that often carry little significance for our analysis, using NLTK's built-in stop words list. Finally, we apply lemmatization, which reduces each word to its base form, enhancing the model's ability to generalize. The function then returns a cleaned string, which, trust me, significantly improves the readability and quality of text input for further NLP tasks. For example, this function will process the sentence, "Natural language processing is vital for AI advancements to yield a more meaningful representation for analysis." Now, let's see how we can implement TSNE for visualizing word embeddings. First, we're going to import the necessary libraries. So we'll bring in TSNE from sklearn.manifold for the dimensionality reduction, and don't forget matplot.pyplot for creating those visual plots that help us see things clearly. Now, let's prepare our dataset by extracting the words and their corresponding embeddings from the Glove model, which we've already loaded. Got that? Great! Next, we'll fit and transform our high-dimensional word embeddings into 2 dimensions using the TSNE algorithm. Now, we specifically set the number of components to 2 here because this allows us to visualize our data in, you guessed it, a 2-dimensional space. And just a heads up, parameters like perplexity and n-iter can really influence the quality of our visualization. They'll help balance our view between local details and global structure in the data. After we've reduced that dimensionality, we're ready to create a scatter plot. Think of it as a map where each point represents a word vector in our 2D plane. The plot's dimensions are based on the distances between those word vectors, so nearby points indicate words that are semantically similar. To make our plot readable, we'll annotate each point with its corresponding word. This gives us a clear picture of the semantic relationships within our embedding space. Finally, we display the plot using plt.show, and there you have it. You'll gain valuable insights into how words relate to one another in a visual format. As we reach the end, it's essential to understand the growing importance of continuous research and development in the representation of text for artificial intelligence. The evolution of models and techniques signifies not just an improvement in technological capabilities, but a broader understanding of human language's nuances and complexities. Each advancement allows AI to deliver better results. Whether that's in understanding textual sentiment, generating coherent responses in conversation, or translating languages with a higher level of accuracy. We live in an exciting time. As practitioners and learners of AI, we have the opportunity to harness this power and make meaningful advancements in the field. So, as you continue your journey with NLP, remember that every word carries weight. Every phrase has context, and every sentence tells a story. The way we represent these can unlock various applications that improve and innovate our interactions with technology. Keep exploring, learning, and applying these concepts.